Hey there guys, welcome to the video. My name is Pushpinder Gill. In this video, we're going to be talking about symmetric matrices, right? So we're going to be talking about symmetric matrices. Now, what is a symmetric matrix, right? So what is actually a symmetric matrix? Let's suppose if I say I have a matrix with these things here, let's suppose this is the matrix and I want to know whether it's symmetric or not, right? Okay, now if I want to know that, so if I say that a matrix is a symmetric matrix, it's gonna follow this definition that the transpose of the matrix will actually be equal to that matrix. So what will I say? That the transpose of the matrix will be equal to that matrix. So if I say this is matrix A, what is the transpose of this matrix? That is going to be root 3, 2 and 3. That is going to be root 3, 2 and 3. This column will actually become this row. This row will actually become this column, and this row will actually become this column, and this row will actually become this column, right? So that means from here we will know that since the matrix A is equal to the transpose of its matrix, that means this matrix is supposed to be a symmetric matrix. So matrix A is actually a symmetric matrix, right? And understand one more thing, a matrix can only be symmetric only if and only if it's a square matrix, because if this is 3 into 3, the transpose is also 3 into 3. So but if this is 3 into 2, the transpose will become 2 into 3 and the matrix will not be equal. So it has to be a square matrix before. So that is all about a symmetric matrix. Let's talk about what is the meaning of a skew symmetric matrix, right? So that's there. So let's understand what is the meaning of a skew symmetric matrix. Now, a matrix is known as skew symmetric matrix. First of all, it has to be a square matrix such that the transpose of that matrix, the transpose of that matrix is actually equal to negative A, right? So the transpose of that matrix is supposed to be equal to the negative of that matrix. So generally a matrix looks like this, and a skew symmetric matrix is going to look like 0. There's going to be a number here A, there's going to be a number here B, there's going to be a number here negative A, negative B, 0, negative C, C and 0. Now I'll explain you why this structure is there, because if you find the transpose of this matrix, you know that this row here is going to become this column here, this row here is going to become this column here, and this row here is going to become this column here. Now you can clearly see that the matrix, the transpose of that matrix is actually equal to the negative of that matrix, because every element is negative of itself. You can clearly see here. So if it's A, it's negative A. If it's A, if it's negative B, then it's B. So and the diagonal is always equal to 0. So the diagonal elements are always equal to 0. Why is that? Because when you do the transpose, the diagonal elements get shifted away. They kind of stay the same, and that means it has to be 0 if this has to be satisfied. So that is the meaning of a skew symmetric matrix. So I suppose you're understanding this point over here. Let's go ahead and understand some of the important theorems, which will actually help us in understanding the symmetric and skew symmetric matrices. So for the first theorem that I'd like to discuss is that for any square matrix, provided that all the entities or all the elements are real numbers, A plus A transpose and A minus A transpose, they're going to be skew symmetric matrices, right? So they're going to be skew symmetric matrices. Let's go ahead and understand that, why this is going to be there. So what I'm going to do here is that, I'm going to pick up a matrix. I'm going to pick up a square matrix. Let's suppose the matrix is 1, 2, 3 and 4, right? So if this is the matrix, then what is going to be A transpose? A transpose is going to be 1, 2, this row becomes this column, and this row becomes this column. Now let's try to find a let's go ahead and try to find that. I'm sorry, the theorem says that A minus A is a skew symmetric matrix and A plus A is a symmetric matrix. I'm sorry about that, right? So that's the theorem. So A plus A transpose is a symmetric matrix, and A minus A transpose is a skew symmetric matrix, right? So if I try to find A minus A star A transpose, that's gonna be 1 minus 1, which is 0, 2 minus 3, it's negative 1, 3 minus 2 is 1, and 4 minus 4 is 0. So this is a skew symmetric matrix because the diagonal elements are 0 and all other elements are the negative of each other. If you know the definition of skew symmetric, that the transpose of A is equal to negative of A. So the transpose of this matrix, so what is going to be, let's suppose this is actually equal to matrix B. So the transpose of B is going to be equal to 0, negative 1, and 1 and 0. That will actually be equal to negative of B. You can clearly see negative of B is equal to this. Another thing that I'd like to test is the value of A plus A transpose, which is going to be 1 plus 1, that is 2, 2 plus 3, which is 5, and 3 plus 2, which is 5, and 4 plus 4, that is 8. Now if I kind of let's say that is equal to B, then again if I try to find the value of B transpose, that is going to be equal to 2, 5, and 2, 5, and 5, 8. The value of B transpose is actually going to be equal to the value of B. You can clearly see that these both are equal. So A plus A transpose is going to be symmetric, and A minus A transpose is going to be skew symmetric. So that's the first theorem. Let's go ahead and understand the second theorem, guys. I suppose you're understanding this. So the second theorem states that any square matrix, so it says that any square matrix can actually be expressed. So any square matrix can be expressed, I'm just gonna write it there so that you keep your focus on, can be expressed as the sum of a symmetric matrix, as the sum of a symmetric matrix and a skew symmetric matrix, right? So that is the second theorem, which states that any square matrix can be expressed as the sum of a symmetric matrix and a skew symmetric matrix. Now how do we prove that? How do we prove this theorem? So we're gonna assume, let's suppose there is a matrix A, which is actually a square matrix, and we want to say that this A over here can be expressed as the sum of a symmetric matrix and as the sum of a skew symmetric matrix. Now let me do one thing here. Now I know that A plus A transpose is actually a symmetric matrix, something that we know from the previous theorem, and A minus A transpose is actually a skew symmetric matrix, right? So that is also there. So we know that A plus A transpose is a symmetric matrix and A minus A transpose is a skew symmetric matrix. Now if I say I want to find the sum of A plus A bar plus A plus A dash minus A minus A dash, that will actually come down to be equal to, that this and this will get cancelled out. We're going to get 2 times A. So that means if I just, divide this by 1 by 2, divide this by 1 by 2, I'm going to get A eventually. So that means I can say that a matrix, a square matrix, can be explained as equal to half of this matrix plus the half of this matrix, right? So that is the theorem which says that a square matrix can be explained as the sum of a symmetric matrix and a skew symmetric matrix. So a square matrix can be expressed as the sum of a symmetric matrix and it can be expressed as the sum of a skew symmetric matrix. This is what the theorem states. Now let's put that to practice here. Let's go ahead and say that we have a matrix. Let's suppose the matrix is this here, which is 2, negative 2, and negative 4. Let's say negative 1, 1, 3, negative 2, 4, and negative 3. Let's suppose we have this matrix and we want to express this as the sum of a symmetric matrix and as the sum of a skew symmetric matrix, right? This is what we want to do. So what we're going to say is, let's suppose B is equal to, we know that B is actually equal to half of B plus B dash plus half of B minus B dash. This is a symmetric matrix and this is a skew symmetric matrix. So let's go ahead and find the value of I'm just going to divide this into 4 parts. Let's go ahead and find the value of B plus B dash. First of all, I need the value of B transpose. So the value of B transpose is going to be 2, -2 and -4. I'm just making this row as a column. I'm making another row as a column, and I'm making another row as a column. And let's suppose we want to find the value of B plus B dash. So the value of B plus B dash is going to be 2 plus 2, which is actually 4, and -1 is -3. This is -3 again. This here is -3 again. -2 and -2. 3 and 3 is 6. 4 and -2 it's 2. 1 and -4 it's -3. And 2 and 4 is actually 2, and 3 and -3 is -6. So this is the value of B plus B dash. And what is the value of B minus B dash? So the value of B minus B dash is actually going to be equal to 2 minus 2, which is 0, -2 minus -1, which is +1, which is -1, -4 and -1 is -5, -1 and negative for -2, it's +2, that is actually equal to 1. 3 minus 3 is 0. 4 minus of -2 is 6. 1 minus of -4 is 5. Then we have a -6 here, and we have a 0 here. Right, so that is what we have. Now, if I want to find this expression here, will that be equal to B? Let's put that to test. So half of B plus B dash plus half of B minus B dash can actually be this over here. If I multiply this by half, everything will actually become half. So this is going to be half of every element here. So I have to multiply this by half. I'll have to multiply this by half. So this is going to be equal to 2, -3 by 2, -3 by 2, -3 by 2, 6 by 2 is 3. Then we have 1 here. Then I have -3 by 2. Then we have a lot of -3 by 2's, by the way. This is 1 and this is -3. Then what I'm going to do is I'm going to add this to this matrix here, which have 0, -1 by 2, and I have -5 by 2. Then I have 1 by 2. Then I have 0. Then I have 3. Then I have 5 by 2. Then I have -6 by 2 is 3. That is 0. Now, if I kind of find the sum here, if I add this with this, what I'm going to get? I'm going to get 2. I add this to this, I'm going to get a -2. I add this to this, I'm going to get a -4. I add this to this, I'm going to get a -1, because that's there. 3 plus 0 is 3. 1 plus 3 is 4. -3 by 2 plus 5 by 2, it's 1, because that 5 minus 3 is 2. 2 by 2 is 1. 1 plus -3 is -2. -3 plus 0 is -3, which is actually equal to B. You can clearly see this matrix and this matrix is equal. That means that I've proven that this is something which is going to remain true all the time, right? So I suppose you're understanding what I'm trying to do here, guys. I'll just summarize what we did in this video. The summary. In the summary, we said that a matrix can be called a symmetric matrix. A matrix is a symmetric matrix provided that it's a square matrix, such that the transpose of the matrix is actually equal to the matrix itself. A matrix is known as a skew symmetric matrix. Again, it has to be a square matrix, provided that the transpose of the matrix is negative of A. And the first theorem that we stated, that A plus A transpose is always a symmetric matrix, and A minus A transpose is always skew symmetric matrix. And the second theorem that we said, that a matrix cannot be written as the sum of a symmetric matrix and a skew symmetric matrix, right? So that is there and that is there. That'll help you in a lot of manipulation. So thank you very much for watching this video, guys. And just make sure that you explore this website that is perfect, and a small -course.com. Make sure that you explore that. And this would be our website address. I've already told you that. This would be the Facebook page to give us your valuable like, and this would be our email address to give us your valuable feedback. You can also find us on Twitter and all the professional social network websites, right? So this would be about this video, guys. Thank you very much for watching. I'll see you.